Welcome to the test sources tutorial, today about the full Bloch-McConnell simulation and fit. So what we want to do is actually the same we did in this article, was recently published in MRM, QUESP and QUEST Revisited. So there we fitted multi B1 Z-spectra, so acquired of a parasist system at different B1 levels, and then fitted them simultaneously with the Bloch equations, also with the analytical QUESP and Omega-plot equations. So that's what we want to do. To do this, just copy from the GitHub again the Bloch-McConnell Simulation and Fit files. So this can be found here, and you just click clone or download and download the whole zip file, or copy it, clone it with your BM-Sim and Fit. So I did that here. And so first of all you have to open MATLAB and put all of them in your path. So select folders and subfolders of this whole folder BM-Sim Fit. Then you go, so all the functions are now loaded in MATLAB and can be accessed, and now you go to the folder documentation, and there you find also a Word file where everything that I say is also documented and explained, and there are two script files, one for fitting and loading data and one for simulations only. So we first focus here on the loading of data and fitting of it. So if you open this, the only function, or the MATLAB function I use is just run by section, so we can always run the section which is defined by such a symbol, and evaluate the data. First of all, we have to load the data, and for this we actually defined a new standard QSest Excel file, which is also here. So we can open outside MATLAB and have a look how is this Excel file structured. So actually first of all we have some parameters set up here, and then finally the multi-B1 and multi-offset data, Z-spectrum data down here. The structure of this file should be always the same. So we have, for example, the experiment name here, the frequency, recover time, which is given here in this plot, T1 time, T2 time as measured, concentration, the M0 scan, so here it is 1 because we're fully relaxed and already normalized data. The initial magnetization is also assumed to be 1 because we're in steady state, it doesn't matter. We normalized the data by -80 ppm, so this we also have to tell our fitting and simulation routines. Then here's the number of offset and B1 values. That is exactly what has to match to this matrix. Of course we can have more B1 values or more offsets, but it has to be a rectangular matrix, and you have to adjust these numbers then. You can also run a pulsed experiment. 0 stands for continuous wave, and then give number of pulses, duty cycle, and the shape. And very important, so this must be row number 1, and then the data starts here. And exactly in the same format you can write different Excel files, or actually have different sheets in the Excel file. So for example here we have parasist data of 15 degree, 25 degree and 37 degree. So with this we can go back to MATLAB and actually go to the first section, which loads such an Excel QSest file and converts it to a MATLAB table, which is called CTab here. So this is the variable. So we can just give the name of the sheet we want to load, so for example the 25 degree, and if we run this here, he asks us for the Excel file, we open it, and all the parameters will be loaded. So he shows what he loaded, and this will be stored in the frequency axis, omega x, C data, which is Cx. All the parameters are stored in this parameter struct P. Then the row name is actually given, this is dota 25, and finally the CTab structure will be created. You don't need this for fitting directly, but it's very convenient, as I will show now. So if you look in CTab, this is like for each quantitative experiment you have such a row in this MATLAB table with the experiment name, the parameters stored nicely, the offset, and the multi-B1 Z-spectra. Yeah. So you can go to 1.2 already with this, but I want to quickly show you that the setup is very convenient. So you can just load all the Excel files, all the Excel sheets if you don't give an argument to this load XLS QSES to ZTAP. So we again run the section, load the full Excel file, and now if we look in the ZTAP, he will actually, first he plots the data, so this is all nice, yes, 37 degree, 25 degree, 15 degree, and here it's now stored in MATLAB in 3 lines, so each line is a full quantitative experiment. Okay, and if we have it in the ZTAP structure, it will be very convenient to just quickly load it and manipulate it. So for example, here I give again, if I look in MATLAB and I take this row name, I can just copy paste it here. So for example, let's take the Dota 25 and put this as a row name here. So he will now load again, if I run this section, from the ZTAP to this omega x and cx, the data that's actually fitted. But we also can perform some corrections on this. So for example, we can do P0 correction or normalization, or exclude some points, or do some other normalization that we gave in the beginning. And if you run this again, you just see the spectrum again that was loaded, and I also see that this is now P0 corrected. Well, in this case it wasn't necessary, but yeah, you can of course get data that needs P0 correction. Okay, so now we have all the data loaded. So the next step is the other side. We have to set up our simulation, and this is done in the section 1.2. And here all the fields that are needed, all the parameters that are needed for the simulation are initialized. Now there are many parameters. You can always read what the actually parameter is that is needed. And for example, most important is if you want to have an analytic function or numeric. For numeric stands for 0, but analytic is much faster now, so that's why we use this. You can also add an MT pool, which is set to 0 here now. And we have 2 CEST pools in the paracest system, one far off resonant and one close to border, an amide pool. Then you can also set up the frequency. However, this measurement parameters are also stored in this parameter struct P, so that one that we just loaded from the ZTAP. And actually this is stronger, so this will override the sim parameters if given. Okay, so there are many more parameters from the setup, just in case of pulsed or continuous wave. But most important are the pool system parameters, because they are not given by the measurement. This is something we assume. So here we assume a 3-pool model, so a water pool and 2 CEST pools. And we have to give the position, so delta omega A, R1A, R2A, so the relaxation of the water pool. Then for each CEST pool we have to give concentration, exchange rate, position and relaxation rates. The same for the amide pool, which is around -5 ppm or so, and this paracest pool is around 55 ppm. Okay, if we run this section, everything is set up. So now we have in the P we have the measurement parameters, and in sim we have all the simulation parameters. Okay, with this we can go on and come to the most important part of the simulation and fit. We have to set up the starting values and boundaries of the fit. So for this we have, for each pool we have such a block where the dependent parameters are defined. So this is again delta omega A and the relaxation rates, and then there's another line which is called vary, t-vary, and it defines if we want to fit or if we want to provide the parameter to the fit. So 1 means we want to fit the peak position or the water pool position. 0 means here for T1 we want to provide the T1 value we measured, so he will take the one from P.R1A and not fit this parameter. R2 on the other side we want to fit it. Alright, so the same for pool B. So again we have the position, concentration, exchange rate, relaxation rate, and all the flags are set to 1, and then we have the starting value here. So starting value for the offset, and actually for the starting value he just takes the value written in sim. So if we define this nicely up here, he will have a good starting value. Yeah, and the lower bound is just the position of the peak position minus 10 ppm and the upper bound plus ppm. Yeah, and so here you see they're quite loose upper and lower boundaries. And this we have to do for each pool. Pool C is here commented. Pool C is always the semi-solid MT pool, so here it is just commented out. And pool D is actually the amide pool, so yeah, again we call it from the sim DVD. And if you look at it, it's yeah, the starting value is around -5. The lower value will be -15 ppm and the upper value -2 ppm. For R2D and R2B as well, we always assume a value between 0 and 50 Hertz. Well, this is actually very hard to measure. I don't know if there's good values for that, but we assume if we exclude the exchange or have the exchange explicitly fitted, this should be a dipolar value and relatively low. Okay, with all the starting parameters, they are stored in another struct, which is the fit struct, which contains all the parameters, like also the simulation, starting values, and all the parameters of the fit. Alright, so now the simulation is set up, the fit has a starting value, and if we run this section now, he will plot both. He will plot the data, omega x and cx, and also the simulation of the starting values. So if we do this, we see we actually have quite good starting values. The peak is a little too broad around water, and it's a little too low here, but it will be a very nice starting value actually. So now everything is set up. Of course you can play around with the parameters here, but now you can just start the multi-Z fitting. So this is section 1.4, and if we run this, he will now fit quickly and give back the results. And you see here now the summary of all we did. So we set up the simulation, then we overrode some parameters by measured parameters, or really set parameters, in the parameter struct P loaded from the Excel file. Then we have the free fit parameters and the lower and upper like starting values, lower boundary, upper boundary, and finally we have here the fitted parameters, and the line is here the fit, and you see that we have an exchange rate of around 7,000 for this Dotam-Glee at 25 degrees. Alright, great. So you can actually save this figure and you have all the information of the fit you need. But you can also go on in the script. First of all, we also added the single offset results. So we do QUESP and Omega-plot evaluation. And for this you have to provide the single offset you want to evaluate. So in this example we actually use the fitted position of delta omega b. And just if you run this section, he will fit again the B1 dispersion or the omega plots of the same data. So the used label and reference data is depicted here, and you see the QUESP and inverse QUESP and the omega plot fits with the results, and also we get a exchange rate, well here more or less 6,000, little bit higher, so we don't get the same value as for the full Bloch-McConnell fit, but we're also just using a single value here. Alright, so with that we're quite far. So again, you can save the figure, but you can also just save the C tab now, because all the data is also stored in the C tab. So you see, for example, for the 25 degree, we just created a struct for the fit3 pool, and there's all the parameters stored. Also for the QUESP, the inverse QUESP, and the omega plot, the fitted values together with the boundaries, confidence intervals are stored. Okay, so to go on quickly, we just go for the 15 degree data and also so load this, and we get the data. So we set up the same simulation, we set up actually the same starting values, we run the fit, get the result, we run the single offset result, and we get for 15 degree value about 3000 Hertz. So now the only one missing is the 37 degrees, so I just turn the flag to 37 degree here and run it again, run the same simulation, run the same starting values. Well, it will still find it. We could adjust it, but let's see if he makes it. And yeah, he fits quite nicely, and we get a exchange rate of about 20,000 at 37 degree here. Again, if we do the single offset evaluation, we get also, well, about 16,000 here, so a slightly lower estimation. And now everything is stored in the CTAB, so we have now in the CTAB we have the full quantitative data set, we have all the fit parameters, the fitted parameters for Bloch-McConnell fitting, for QUESP, inverse QUESP and Omega-plot. We also have all the simulation parameters and starting values and everything stored in the CTAB. So now if we save the CTAB in the next section 1.6, yeah, I just overwrite this one. We have all the data stored, so I can just clear that now, clear the workspace, load my CTAB again, and with section 1.7 I can just, for example, load the 25 degree data again and plot the fit results. Okay, there's still the guess in there. Run it again, plot the fit results, and I have the full plot again. I didn't plot the QUESP and Omega-plot, but you can just run this section again, and there you have it. Yeah, there you go. So with the CTAB, now you have saved everything. Alright, so the final thing you want to do is you want to plot the different rows, for example, in the CTAB. So you want to plot 15, 25 and 37 degree. Yeah, and to do this you just have to go to index of the rows, give the different temperatures as an x-axis, and this is now loaded automatically and stored. And if you run this section, you get actually the exchange rate as a function of temperature, and you see, okay, we get a pretty nice match between Omega-plot and QUESP, but the Bloch-McConnell fit seems to be a little bit more accurate, lower error bars and a little bit higher. Alright, that's it. And of course I want to quickly show that you can also do it just with a single Excel sheet, so you don't need to run the full thing. You can just run like one sheet, 15 degree. Yeah, so now again this is the data, it's directly stored in this, so we can directly jump to 1.2, run this, set up the simulation, starting values, okay, they will be fine, run the multi-C spectrum, get it back, and can store this figure and have everything stored. Of course we can also do the single offset for this, and everything is stored. Anyways, I always work on the CTAB, so now you have a single line CTAB which you can store of course as well, but yeah, if you have a lot of data you can just fill this MATLAB table and be happy. Alright, so just a short summary. If you load everything to this quantitative Excel file exactly in the right order, so don't change any fields there, then you can use the scripts to load the Excel file, or like many sheets of the Excel file, to this CTAB structure, and then just run exactly the same fit on that. Everything is stored in the CTAB structure, and you have a full quantitative data stored in one file, and you can always reproduce what you did, and you can always have a look what starting values you used.